Hi everybody, so you need your guided note pages. We've been working on the pH portion, which is page 1, and what I'd like to do is go a little bit over again the characteristics of acids and bases, how to recognize them, as well as the Arrhenius acid-base model and the Bronsted-Lowry. So again, things you've explored, but I just want to spend a little bit of time reviewing over those with you. So you would need to turn to page 2 of your guided notes, and at some point there'll be some information that you'll need to record. Alright, so I love the idea of looking at some everyday common items to understand how acids and bases are a part of your world. So again, I think most of you are pretty comfortable with the idea that things such as lemons, limes, oranges, your fruits, are weak acids, and they're made up of what's called citric acid. And then another acid that is weak is going to be formic acid, and so that is usually that sting that you feel, the little bit of poison that's put inside of you from something like an ant bite. Aspirin, which most of you probably don't take, but it certainly has its benefits to one's health, especially heart health. It is also a weak acid. And then the wonderful world of caffeine. So many people think that caffeine is actually acidic because it can cause you to have increased stomach acid, but it's actually a weak base. It's actually the pH of it is above 7. And then sea slugs actually secrete sulfuric acid. So just something of interest. Okay, so some of the properties of acids, we've discussed these. So they produce H+ ions in water. That is called a hydronium ion, and the correct way to write that is H3O + 1, but you will see it interchanged as H+ and H3O + 1 because actually a water molecule is picking up the hydrogen ion that's being donated. Taste sour. Their pHs are less than 7. They're good conductors of electricity, so they're considered electrolytes because they break apart into charged particles in solution. They react with metals to produce hydrogen gas. You've seen that quite a bit with hydrochloric acid and magnesium ribbon. You guys have also done zinc. All of those have created H2 as a product. If they react with a carbonate, which we have not done that, we've broken down carbonates, but if they react with a metal carbonate, they produce carbon dioxide gas. And they react with bases to form a salt and water, which is what our ending thing that we're going to do. That's a neutralization reaction, and we'll deal with titrations here soon. And then, of course, they turn blue litmus paper red. So properties of our bases. So they produce the hydroxide ions in water. Bitter, chalky taste, so like baking soda is a great example of something that's a base. They feel very soapy and slippery on your fingers when you have some base on your hands. So like your everyday soap it has sodium hydroxide in it. It helps to slough off those skin cells, those dead skin cells, to clear and clean up your skin. pH greater than 7, they're also good conductors of electricity because they break apart into ions in solution, so that makes them good electrolytes, so they're considered electrolytes. They react with acids to form salts and water, so that's neutralization, and they turn red litmus paper blue. Okay, so there's two models. There's the Arrhenius model, and then there's the Bronsted-Lowry model. So, the Arrhenius model states that acids produce H+ ions when they're dissolved in water, and that bases produce hydroxide ions when they're dissolved in water. Those are beautiful definitions, but they certainly have their limitations, because the problem is that some bases don't have hydroxide ion as a part of their formula, but they're still considered a base. So this model was limited, even though its early explanations were very true. So a few examples of a couple of bases. I think it would be great to have those. Ammonia is a base, NH3, so it's not made up of hydroxide ions within its formula, but it does accept hydrogen to become an ammonium ion. Sodium carbonate is also a great example of a basic material, and as you can see, it also does not have hydroxide ion as a part of its formula. Okay, so here's just a model here of arsenous acid. It's showing here what's happening. So you can see here we have our hydrochloric acid, which is an acid because it has hydrogen in the front. Its name suggests that it's hydrochloric acid. And then we also know that what it does is it's donating its hydrogen to the water molecule so that over here we become H3O plus and a chloride ion. So an arsenous base is a substance that produces hydroxide ions in water. So you can see here that when I take sodium hydroxide and it dissolves, it breaks apart into Na plus and OH minus. And then here's just a few more examples. Acid, you can see here, produces H plus ions in solution. Most bases produce hydroxide ions in solution. And here we can see salts also ionize. So all of these are good conductors of electricity as well as good electrolytes. Okay, so let's move on to the Bronsted-Lowry model, which was able to further explain acids and bases with relationship to their behavior. Okay, so this model focuses on the hydrogen ion and what's happening to it. Is it donating itself to something and the other thing is accepting it? And this helped us really better explain why other items were considered bases, like ammonia. So let's change our language. So now we say that acids are proton donors and that the bases are the proton acceptors. You could also say that the acids are hydrogen ion donors. You could likewise say that bases are hydrogen ion acceptors. We've discussed all of this through that POGIL activity. I just would definitely make sure that we review this again. And plus we had that whole problem we worked out on the board. We labeled everything. I hope you took a picture of that so that you can imprint that in your mind. So let's look here at this problem. We have ammonia and water, and what we need to do is discover what's going on when we get to the product side. So if we look at this first material, NH3, when you get over here and see how it's behaving, you see that it accepted a hydrogen ion, which means this is acting as a base. And water is acting like an acid because it is donating one of its two hydrogens to the ammonia to become these products. Okay. So we also talked about conjugate acid and conjugate base. And we know that the conjugate acid is the species that's formed when the base accepts a hydrogen ion, and the conjugate base is a species that results when an acid donates a hydrogen ion. So what I like to do, remember I drew an arrow from here over to the NH4 because these are the two species that are similar. So we went ahead and decided that this was the base because it ends up accepting a hydrogen, which makes this the conjugate acid. Because in the reverse reaction, isn't this particle going to give up its hydrogen, right, to this guy to become the water? So likewise, the water, I draw an arrow from here to here. And so this is the acid, which makes the hydroxide ion the conjugate base. And when you move backwards again, we definitely see that this ammonium ion donates one of its hydrogens to the OH to make the starting materials again. Base, acid. So this is the conjugate acid, conjugate base. Okay? Right, and just another sample of looking at things that are donating and receiving. So we can see here we've got acetic acid. It's going to donate its hydrogen ion to the water molecule. Okay, so this is acting as the acid on this side. This is acting as the base this time. So now this time water is acting like a base. So water can act like an acid and a base, which is amazing. Over here we have H3O plus, and then we have our acetate ion. So these two species are similar. If this is the acid, this becomes the conjugate base. And if this is the base, this becomes the conjugate acid. Thank you.